Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to close your eyes for a second. Well, assuming you're not driving, obviously, and just really put yourself in this scenario. Imagine you're standing on the surface of another world.
It's a pretty wild thought experiment.
Right. Like maybe it's the icy, cracked, just blindingly white crust of Jupiter's moon Europa. You can actually feel the vibration of the ice groaning under the gravitational pull of that massive gas giant hanging in the black sky right above you.
Or, you could be standing on the dusty, rust-red surface of Mars.
Yeah, looking out over this desolate, wind-scoured crater that hasn't seen a drop of liquid water in, a billion years?
It's easily a billion years, yeah.
So you're standing there, and you have been given one job. It is, without a doubt, humanity's biggest, most profound question, which is, are we alone?
And that right there is the question that drives the entirety of planetary science. I mean, it's arguably the most difficult scientific question to definitively answer.
Because of the scale.
The scale of space, absolutely, but also the microscopic nature of what we are actually looking for.
Right, because here's the massive catch. How do you actually prove that life exists or, existed when you can't just reach out and touch it?
When you can't see it with your own eyes.
Exactly. When it doesn't leave behind a convenient little fossilized skeleton for a rover to just dig up. We are talking about microscopic, ancient, incredibly elusive traces of biology.
Which brings us to the core of what we're talking about today.
Yes. The mission for our conversation today. We are exploring a groundbreaking, just absolute paradigm shift in astrobiology. Because for the longest time, we've been searching for these individual, specific, magic molecules.
Right, the chemical signatures we thought would just definitively prove life is present.
But now the field is undergoing this incredible pivot. The focus is shifting away from those individual magic molecules, and instead, the search is zeroing in on hidden statistical patterns of organization.
And honestly, the implications of this shift require us to completely rethink our assumptions. For decades, the fundamental approach to searching for life has been, highly reductionist.
Meaning what exactly?
The thought process was that if we look at the individual pieces of the puzzle, the presence of certain pieces guarantees the existence of a biological picture.
Okay.
We've been looking intensely at the individual pieces of hay rather than how the entire haystack is organized.
Okay, let's frame this shift because it completely changes the game. Imagine you are looking for a needle in a cosmic haystack. For decades, we've been trying to build better and better metal detectors to find that one specific needle.
Right.
But what planetary scientists and researchers are realizing now is that we might need to stop looking for the needle entirely. What if we are looking for the way the hay itself is organized? Because life doesn't just leave a needle, it rearranges the haystack.
That's a great way to put it. We have to fundamentally redefine life, not just as a collection of specific chemicals, but as an active organizational principle.
An organizational principle.
Yeah. If you take every single chemical compound that makes up a human being, the carbon, the water, the trace minerals, and you just put them into a vat, you do not have a human being.
You just have a really gross, chemically complex soup.
Exactly. Life is a process. It is a system that takes chaotic, random matter and energy from its environment and organizes it with striking intent to maintain its own existence.
And what the latest research in astrobiology demonstrates is that this organizational principle leaves a distinct mathematical fingerprint.
It creates a statistical pattern in the chemistry that we can actually detect and, more importantly, quantify.
And the reason this matters to anyone listening right now is that you are getting an insider's view of planetary exploration crossing a massive threshold.
It's a huge moment for the field.
It really is. For generations, questions about the origin of life, how prevalent it is in the universe, whether it exists in the subsurface oceans of Enceladus or like the permafrost of Mars, these were largely philosophical debates.
But those ancient questions are finally becoming testable. We are looking at real, tangible observational data through a completely new lens.
So to understand why this statistical approach is so necessary, we first have to look at the limitations of the old way of doing things.
Right, the previous paradigm. The traditional approach of simply looking for the ingredients of life has effectively hit a brick wall.
Which in astrobiology circles is often referred to as the molecular mirage, right?
Yes, the molecular mirage. It's a very fitting name.
So for decades, the holy grail of astrobiology was finding specific organic molecules. And the logic seemed pretty sound, right? Life on Earth is built on certain foundational blocks.
Sure, we have amino acids, which link together in incredibly complex chains to form proteins. And proteins basically do all the heavy lifting in our bodies.
And then we have fatty acids, which make up the lipid bilayer membranes of our cells.
Right, they hold the biological machinery inside and keep the chaotic environment outside.
So the prevailing assumption was that if we find amino acids or fatty acids on Mars, or drifting in the icy plumes shooting out of a moon like Enceladus, boom, we found life.
But the logic was based entirely on Earth-centric biology. Biology here uses these specific compounds universally. A bacterium deep in a hydrothermal vent and a blue whale use the exact same fundamental chemical building blocks.
So the assumption was that finding these specific molecules elsewhere in the solar system would just be a definitive biosignature.
Exactly. But the universe turned out to be far more complicated and honestly far more chemically creative than we gave it credit for.
Because we now know that these exact same compounds, these core building blocks of life, can form through completely non-biological processes.
Right. They don't need a living cell to synthesize them. We call these abiotic processes.
Abiotic simply meaning without life.
Yes. The basic laws of chemistry and physics, operating in the incredibly harsh conditions of deep space, are perfectly capable of synthesizing complex organic molecules.
Which is so wild to me.
It's fascinating. You have raw carbon, hydrogen, oxygen, and nitrogen drifting in interstellar dust clouds. When these basic elements condense onto microscopic ice grains and are bombarded by ultraviolet radiation from young stars...
The energy from that radiation just breaks the chemical bonds.
Exactly. The atoms recombine randomly. Over millions of years, this entirely random, cold, dark process builds up amino acids and fatty acids.
And they've literally synthesized these molecules in laboratories on Earth, right? Like, scientists have built these high vacuum chambers, cooled them down to near absolute zero to mimic deep space.
Pumped in basic gases, hit them with simulated cosmic rays, and the result is a chemical soup containing amino acids.
And it's not just a laboratory trick. We have physical proof that this happens naturally. We have actually found these organic molecules on meteorites that have crashed to Earth.
The Murchison meteorite is the textbook example of this.
Oh yeah, the one in Australia.
Right. In 1969, a massive fireball streaked across the sky over Victoria, Australia, and showered the town of Murchison with fragments of rock.
And this wasn't just any rock.
No, this was a carbonaceous chondrite. It's a primitive relic left over from the very formation of the solar system over 4.5 billion years ago.
So when analytical chemists got their hands on these fragments and ran them through their instruments, they were stunned.
They found dozens of different amino acids locked inside the rock.
Okay, wait, I want to challenge the perception here for a second. If a meteorite crashes to Earth and scientists cut it open and find it is physically carrying amino acids, the literal building blocks of proteins, why wasn't that the biggest headline in human history?
That's the million-dollar question.
Right, like if the building blocks of life are falling from the sky, doesn't that inherently mean life is everywhere?
It means the chemistry required for life is everywhere, but chemistry is not biology. That is the fundamental disconnect.
Okay, unpacking that.
Finding amino acids on a meteorite proves that the universe is highly proficient at making complex carbon molecules. It does not prove that those molecules were ever part of a living system.
Let me try to put this into an analogy to make sure the mechanics make sense. If I walk into a kitchen and I find a bag of flour, some sugar, and some eggs sitting on the counter, I can't just assume a baker has already been there and baked a cake.
Right, exactly.
Finding the ingredients alone doesn't prove the action of baking has occurred. The flour and sugar exist completely independently of the cake. So the universe is essentially a very messy kitchen, and it's constantly spilling raw ingredients across planets, moons, and asteroids.
And that messy kitchen creates an agonizing problem for astrobiologists. When a rover analyzes a soil sample on Mars and detects a complex organic molecule, the science team is immediately faced with a brutal forensic challenge.
Did this molecule come from a biological baker-like an ancient Martian microbe that died billions of years ago? Or was it just synthesized by the random abiotic chemistry of a meteorite that struck the planet's surface?
I love that phrasing, the forensic challenge, because we aren't just biologists looking through microscopes at swimming cells. We are cosmic crime scene investigators trying to solve a billion-year-old cold case.
It really is like CSI, Mars.
Think about the mechanics of forensic science. Investigators arrive at a scene long after the event. They do not have a video recording of what happened.
You just have the aftermath.
Right. They have to infer incredibly complex dynamic processes from scattered static clues, a microscopic drop of blood, a specific fracture pattern in glass.
And astrobiology operates on the exact same principle. But the crime scene is an alien world millions of miles away, and the evidence has been subjected to extreme radiation and geological weathering for eons.
And the investigators are doing this work entirely by remote control. The stakes and the limitations of these space missions make this false positive problem incredibly tense.
Oh, absolutely. We're talking about flagship missions that take 20 years to design and billions of dollars to launch. You put a rover on top of a rocket, blasted into the vacuum of space. It survives the terrifying 7 minutes of terror plunging through the Martian atmosphere.
And finally, it drills into a rock in the Jezero crater. The data comes beaming back to Earth. The mass spectrometer shows a clear, undeniable spike for an organic molecule.
The initial reaction is always excitement, right?
Always. But it is immediately followed by a profound scientific paralysis.
Because of the burden of proof.
The burden of proof required to claim the discovery of extraterrestrial life is astronomically high. You cannot announce to the world that you have found life based on a molecule that we know can be created by a lifeless rock floating in space.
So the mission is a massive success in terms of identifying the chemistry of the planet. But it's an agonizing cliffhanger in terms of answering the biological question. We fundamentally lacked the tools to prove the molecule came from a living thing.
And that paralysis is what drove the field to search for a new paradigm. Relying solely on the mere presence of specific molecules was a scientific dead end.
We needed a signature that abiotic chemistry simply could not mimic.
Exactly. We needed a method to distinguish the chaotic, random thermodynamic output of a messy universe from the highly ordered, intentional output of biological life.
Which brings us to the most unexpected leap in this whole endeavor. If looking at the chemical pieces isn't enough, astrobiologists needed a radically new way to interpret the data. And the solution didn't come from a deeper understanding of planetary physics.
No, it didn't.
It came from an entirely unexpected field, right? Ecology and human history.
This represents the power of cross-disciplinary science. What's fascinating here is that the researchers leading this new approach realized that a framework already existed for quantifying complex systems. It just wasn't being used in chemistry.
Where was it being used?
It was being used by ecologists to measure biodiversity in rainforests and by anthropologists to study ancient human settlements.
Okay, let's look at the mechanics of this ecological framework. In ecology, if you want to understand the health or the complexity of a specific environment, you don't just count the total number of trees or animals, you measure the biodiversity.
Right.
And biodiversity is quantified by two specific statistical properties, richness and evenness.
Richness is essentially a measure of variety. It asks the question, how many different types or species are present in a given sample?
So if you map a section of the Amazon rainforest, the richness is staggering. You might catalog hundreds of different species of plants, insects, and mammals in a single acre.
Exactly. But if you map a section of the Sahara Desert, the richness is drastically lower.
So richness equals the number of unique categories.
Yes, but richness alone doesn't paint the full picture of an ecosystem. That is where evenness comes in.
Okay, explain evenness.
Evenness measures the relative abundance of those species. It asks how uniformly the different species are distributed.
So how many of each type?
Right. Let's say you have two different forests, and both forests contain exactly 10 different species of trees. Their richness is mathematically identical.
10 species each. Got it.
However, in the first forest, 91% of the trees are pines, and the other 9 species make up just 1% each.
So it's mostly just a pine forest with a few stragglers.
Exactly. That distribution is highly skewed. It has very low evenness. In the second forest, each of the 10 tree species makes up exactly 10% of the total population. The distribution is perfectly uniform.
That is a high evenness.
You've got it.
And the leap of logic here is just wild. Because researchers originally used these exact diversity metrics to uncover patterns not in forests, but in ancient human cultures.
Yes, applying this statistical math to archaeological data. They were analyzing the distribution of human artifacts, Tools, pottery shards, settlement structures.
And the mathematical patterns reveal that human culture organizes its environment in a highly specific way.
Human activity leaves a distinct statistical pattern of richness and evenness that is entirely different from the patterns created by natural abiotic forces like water flow, wind erosion, or random chance.
Here's where it gets really interesting. Let's try to visualize this concept of statistical organization because it is the linchpin of the entire theory. Think about the difference between an untouched natural wilderness and a major metropolitan city.
Okay, I like this.
If you are standing in a rugged, uninhabited mountain range, the materials around you, the rocks, the dirt, the veins of quartz, are scattered completely randomly. Their distribution is dictated by chaos, weather, and tectonic shifts.
It's an abiotic distribution governed by physical forces. The materials are in a state of thermodynamic equilibrium. They settle wherever gravity and energy dictate.
Right. But if you shift your view to a city like Tokyo or New York, the materials are no longer scattered randomly. The steel, the glass, the concrete, they are organized with striking statistical intention.
Intentional design.
Exactly. The steel is concentrated in vertical columns to build skyscrapers. The asphalt is laid out in long, continuous, perfectly even strips to create grid-like roads. The glass is evenly distributed in rectangular sheets on the sides of buildings.
The patterns are obvious.
If an alien intelligence observed Earth from orbit, they wouldn't need to know what a human is or what a skyscraper is used for to realize that the distribution of steel and glass in a city is statistically unnatural. The highly specific organization of the materials is the mathematical proof of an organizing force.
The city is the macro-scale equivalent of organized chemistry. Biological life organizes the microworld of carbon, nitrogen, and amino acids the exact same way human intelligence organizes steel and glass.
Life fundamentally creates order out of chaos.
It takes raw energy and uses it to actively fight against entropy, building complex, structured, highly ordered systems. The hypothesis was that this biological order must leave a mathematical footprint in the chemistry itself.
But how exactly did they apply this to molecules? Like, how do you actually apply forest math or city math to a microscopic soup of chemicals? How do you measure the richness and evenness of a molecular sample taken from a rock?
You use an instrument called a mass spectrometer.
A mass spec.
This is the workhorse of analytical chemistry, and it's basically a highly sensitive molecular scale. When a sample is fed into a mass spectrometer, whether in a university lab or inside a rover on Mars, it is vaporized and ionized.
Meaning the molecules are given an electrical charge?
Correct. These charged molecules are then accelerated through a magnetic field.
And because they're moving through a magnetic field, their flight paths actually bend, right?
Yes. The magnetic field bends their trajectory. Lighter molecules get bent significantly, while heavier molecules have more momentum and resist the bend. They eventually strike a detector.
And the instrument records exactly where they hit and how many hit there.
The output is a mass spectrum, a graph where the x-axis is the molecular weight and the y-axis is the abundance, or how many of those specific molecules were detected.
So that graph is your forest.
Exactly. The peaks on the graph represent the different species of molecules. The number of unique peaks is your richness, and the relative heights of those peaks compared to one another gives you your evenness.
It allows you to take a chaotic chemical soup and instantly translate it into the ecological metrics of biodiversity.
And having established this framework, the researchers needed to prove that it actually worked on real, messy, chaotic chemical data.
Right, they had to put it to the test. They designed an absolutely massive analytical experiment. They gathered roughly 100 disparate data sets to test this model.
They needed to ensure this wasn't just a mathematical trick that only worked in perfectly controlled lab conditions. So they analyzed data from living microbial cultures. They looked at diverse soils from around the Earth. They analyzed ancient fossilized biological samples.
And they compared all of that against entirely abiotic data.
Right. Meteorites that fell from space, data collected from asteroids, and purely synthetic chemical soups created in laboratories to mimic the conditions of the interstellar medium.
They threw every possible variation of chemistry at this statistical model to see if the math could reliably sort the living from the dead. So let's dive into the actual findings, starting with amino acids. When they ran the math on materials created by living things, they found a very specific pattern.
Yes, in biological samples, the amino acids were consistently highly diverse and highly evenly distributed.
So biology produces a high richness and a high evenness of amino acids.
The reason comes down to biological utility. Living organisms require a wide variety of specific amino acids to fold complex proteins. They actively synthesize and maintain a relatively balanced inventory of these varied amino acids because they are all necessary cogs in the biological machine.
But when we look at the abiotic samples, the meteorites and the lab-synthesized space environments, the pattern for amino acids is completely different.
The abiotic distribution is highly skewed. It has very low evenness.
Why is that?
This is entirely dictated by the laws of thermodynamics. In a cold, random, lifeless environment, forming a simple molecule requires very little energy. Forming a complex molecule requires significantly more energy.
Oh, that makes sense.
Thermodynamic reality means the simplest amino acids, like glycine, form incredibly easily and in massive quantities. As you look for more complex amino acids, the abundance drops off a cliff.
So a mass spectrometer readout of a meteorite would show a gigantic skyscraper peak for glycine, and then just tiny scattered bumps for anything more complex.
Yes. The sheer randomness of abiotic chemistry cannot overcome the thermodynamic energy barriers required to build complex amino acids in high quantities.
But life can?
Life, however, has enzymes. Enzymes are biological catalysts that lower those energy barriers, allowing life to synthesize exactly what it needs, regardless of how thermodynamically difficult it is. Life smooths out the curve, creating the high evenness.
Okay, so for amino acids, life creates an even, diverse spread. But here's where the data gets incredibly fascinating. Because when the researchers looked at a different class of molecules fatty acids, the entire statistical pattern flipped completely.
The reversal in the data is what makes the statistical method so robust. It proves that the mathematical signature isn't just a blanket rule that life is always evenly distributed.
The pattern depends entirely on the biological function of the specific molecules being analyzed. So what does this all mean for fatty acids? Let's break down this reversal. The researchers found that abiotically produced fatty acids, the ones made by pure thermodynamics without life, are distributed more evenly than the fatty acids produced by living biological processes. Why would life create such a drastically different organizational pattern for fatty acids compared to amino acids?
It comes down to what fatty acids are actually used for. Fatty acids are the primary structural components of the lipid bilayer, the cell membrane that encapsulates every living cell on Earth.
The outer skin of the cell.
Right. This membrane is the ultimate biological tightrope walk. It has to be fluid enough to allow nutrients to pass in and waste to pass out. But it has to be structurally stable enough that it doesn't just dissolve, and it can't be so rigid that it freezes solid when the temperature drops.
It's the wall that protects the city.
And to build a stable wall, you need identical bricks. Life cannot maintain that delicate membrane balance using a random assortment of fatty acids of varying lengths and shapes.
So biological organisms selectively synthesize and hoard massive quantities of very specific fatty acids.
The word hoard is perfect here. It implies intense selective intent.
Let me try an analogy to explain the mechanics of this hoarding. Imagine, like, a kid dumping a massive bucket of Lego bricks onto the floor.
Okay, I can picture that.
If you let gravity and random chance dictate how they scatter, which is our abiotic thermodynamic process, the smallest, simplest pieces, the tiny 1-peg and 2-peg bricks, will fall and distribute themselves fairly evenly. There will be a smooth mathematical curve of abundance based on the size of the pieces.
Right, just physical scattering.
But biology isn't a random bucket dump. Biology is a master builder. The master builder ignores the tiny pieces and meticulously sorts through the pile to hoard only the specific 4-peg blue bricks because they are building a very specific, structurally sound wall.
That captures the mechanism perfectly. In cellular biology, the enzymes act as the master builder. They bypass the random thermodynamic assembly and selectively churn out enormous quantities of fatty acids with very specific chain lengths, typically 16 carbon atoms or 18 carbon atoms long.
Because those specific 16 and 18 carbon chains fit together perfectly to build the cellular wall.
Correct. So when you run a biological sample through the mass spectrometer, you don't see a smooth curve. You see massive spiky peaks at exactly C16 and C18 and almost nothing everywhere else. It is intensely uneven.
And conversely, when you look at the abiotic lifeless formation of fatty acids on a meteorite, there is no biological imperative to build a wall.
The carbon atoms just link together randomly, one after another. Forming a 2-carbon chain is easy. A 3-carbon chain is slightly harder. A 4-carbon chain is harder still.
Because the activation energy required to add each subsequent link gets statistically less likely in a random environment.
Exactly. The result is a smooth, evenly distributed, exponentially decaying bell curve. You get a lot of C2, slightly less C3, slightly less C4, all the way down.
So the abiotic distribution is highly even.
The abiotic distribution is highly even, and the biological distribution is intensely spiky and uneven because life selectively hoards the specific shapes it needs for survival. Life is picky, thermodynamics is not.
And this pickiness leaves a permanent mathematical shadow. When the researchers applied this logic across the 100 disparate data sets, the ecological metrics of richness and evenness cut through all the environmental noise.
They were consistently able to separate the biological samples from the abiotic samples with striking reliability.
Which is amazing.
The reliability across such diverse environments, from asteroids in the vacuum of space to soil on Earth, is what suggests we're looking at a fundamental law of biological organization. It implies that the underlying mathematical principles of organization might be universal.
Which opens up a huge avenue for speculation. If it's a universal law of organization, it shouldn't matter if the life is based on the carbon biochemistry we are familiar with, or some exotic alien biochemistry that uses completely different chemical building blocks.
If an entity has to organize matter to build structures and fight entropy to survive, it should leave this specific mathematical footprint. That is the theoretical strength of moving away from magic molecules to statistical models. We are no longer strictly bound to Earth's specific chemical recipe.
But there is a massive hurdle we have to address. It is one thing to easily identify a living, breathing microbial colony today, or a fresh biological sample from a lab. The biological machinery is active, the enzymes are churning, and the chemical organization is pristine.
Right.
But we are not expecting to find active living biology on the surface of Mars. Mars lost its magnetic field and its thick atmosphere billions of years ago. The surface is bombarded by intense ultraviolet and cosmic radiation. If life ever existed there, it has been dead for an incredibly long time. We are looking for the microscopic remains of ancient life.
And the problem of degradation is the ultimate test for any proposed biosignature. Over geological timescales, millions or billions of years, biological molecules do not just sit there perfectly preserved.
That'd be great.
They are subjected to diagenesis, the process of turning into rock.
If we connect this to the bigger picture, I want to dig into the actual mechanics of this degradation. What physically happens to an amino acid or a lipid bilayer over, say, 60 million years buried in rock?
The delicate physical structures are utterly obliterated. The heat and pressure from being buried deep underground cause chemical bonds to snap.
Right.
Cosmic radiation acts like microscopic shrapnel, breaking the long carbon chains apart. Water percolating through the rock can dissolve and transport components away. The complex proteins unravel and shatter into fragments.
The cake hasn't just been eaten. The crumbs have been subjected to a blowtorch, swept up, and buried in a landfill for an eon.
Exactly.
If the physical molecules are destroyed, how can the mathematical signature possibly survive?
This is where the research provided a truly monumental finding. They tested the method on fossilized dinosaur eggshells.
Dinosaur eggshell.
Yes, these samples were tens of millions of years old. The intact proteins were completely gone. The biological matter was heavily, heavily degraded.
So they put this ancient, shattered molecular rubble into the mass spectrometer.
And what they discovered is that even after the physical destruction of the molecules, the statistical organization persisted.
Seriously?
Yes. Think of the glass skyscraper analogy we used earlier. If a massive tornado hits the city and the skyscraper collapses, the physical structure is destroyed.
It's just a pile of debris.
But if you analyze the rubble, you do not find a random, abiotic distribution of silica dust and unrefined iron ore. You find massive piles of shattered glass fragments and twisted steel girders.
I see.
The building is gone, but the proportional abundance of those specific materials, the statistical shadow of the building's original organized design remains.
The structural bonds are broken, but the fragments still retain the original non-random distribution footprint.
The mass spectrometer peaks might flatten out a bit or shift toward lighter molecular weights as the chains break into smaller pieces, but the overall mathematical evenness metric still fundamentally flags as unnatural compared to a random meteorite.
The statistical signature, shaped by the ancient life process, is robust enough to survive the physical destruction of the molecules themselves. The dinosaur is long gone, the eggshell is turned to stone, but the math is still detectable.
It's a phenomenal discovery.
This acts like a ghost hunter for astrobiology. We have rovers operating right now in the Jezero crater on Mars, an area that geologists confirm used to be a massive liquid water lake billions of years ago.
Right.
If a rover drills into a core of sedimentary rock that once held a thriving colony of microbial life 3 billion years ago, the biological matter is pulverized. But this method acts like a ghost hunter, finding the statistical phantom of life left behind in the chemistry.
It allows planetary scientists to peer back through deep time, penetrating the fog of geological degradation, to perceive the distinct shape of biology.
Okay, so we have this paradigm-shifting method, we have proof that it works across diverse chemistry, and we have proof that it survives the extreme ravages of deep time. The final question is, how quickly can planetary science actually deploy this out in the solar system?
That's the best part.
Because historically, in space exploration, a new idea means waiting 40 years for a new spacecraft to be conceptualized, funded, built, and launched.
The incredible logistical hurdle of space exploration is the primary bottleneck for astrobiology. Designing a brand new instrument requires overcoming intense engineering challenges. You have strict weight limits, severe power constraints, and the instrument must be ruggedized to survive the extreme vibration of launch and the thermal shocks of deep space.
It takes decades.
Getting a new piece of hardware onto a flagship mission is easily a multi-decade endeavor and costs billions of dollars.
So if this new statistical method required a brand new, hyper-specific richness and evenness detector machine to be engineered from scratch, we wouldn't see it utilized in our lifetimes.
But that is perhaps the most practical and thrilling aspect of this entire breakthrough. It does not rely on any one special instrument. Because this fundamental principle of life is detected using mass spectrometry, it utilizes the exact instruments that are already aboard current and planned space missions to Mars, Europa, and Enceladus.
Let's talk about the specific hardware, because this is so cool. We have the Curiosity rover driving around Mars right now. It has an instrument suite called SAM sample analysis at Mars.
Right. SAM includes a gas chromatograph and a mass spectrometer.
So it's already there.
The rover scoops up Martian dirt, drops it into a tiny oven inside the instrument, bakes the dirt to vaporize the organic compounds, and then runs those gases through the mass spectrometer. It weighs the molecules and beams the mass-to-charge ratiographs back to Earth.
It's already generating the forest of data.
Exactly. And the same goes for the instruments planned for the near-future missions. The Europa Clipper mission, which is designed to analyze the icy crust and potential subsurface ocean plumes of Jupiter's moon Europa, carries highly advanced mass spectrometers.
This means we don't need a multi-billion-dollar hardware mission. We just receive a software and analytical upgrade. The raw data beaming back from the rovers kicking up dust on Mars right now can immediately be run through this ecological statistical lens.
It's incredibly rare to get a paradigm shift that acts as a software upgrade rather than requiring new hardware.
It retroactively turns every existing data set we've ever collected, from an icy moon or a Martian crater, into a fresh treasure map. We don't need to build a new ship. We just finally figured out how to properly read the map we've been holding the whole time.
The archival data potential is staggering. Space agencies possess massive databases of chemical spectra collected over decades. It is entirely possible that we have already detected the statistical signature of life in past missions.
Wait, really?
Yes, but we simply didn't recognize it because our analytical algorithms were hardwired to look for individual molecular needles rather than analyzing the richness and evenness of the hay.
That is an incredible thought. The answer might already be sitting on a hard drive somewhere, just waiting for the right math to unlock it.
It's a very real possibility.
Let's synthesize the journey we've taken today. We started with the immense challenge of astrobiology, the flawed forensic hunt for individual magic molecules, like amino acids, which we discovered can easily be spoofed by the molecular mirage of abiotic thermodynamic space chemistry.
Then we saw how the field borrowed the ecological concepts of richness and evenness from biodiversity and ancient human artifact analysis.
Right. Gideon Yoff's work.
Which led to the profound realization that life is an active organizational principle that fights entropy.
And we explored how that principle leaves an undeniable mathematical signature, whether it's the highly diverse, even spread of biological amino acids, or the intensely spiky, hoarded, uneven distribution of biological fatty acids built by cellular enzymes.
A signature so mathematically robust it acts as a ghost hunter, surviving millions of years of geological degradation.
However, there is a vital caveat to all of this, right?
Yes. The research team was very explicit in their warnings. As powerful and revolutionary as the statistical framework is, no single analytical method can ever definitively prove the existence of extraterrestrial life on its own.
It is not an absolute silver bullet.
The universe is endlessly complex, and geology can create highly unusual phenomena. Any future announcement claiming the discovery of extraterrestrial life, an announcement that would fundamentally alter human history, will require multiple, completely independent lines of evidence.
So we need this statistical pattern, absolutely.
Right.
But that pattern must be fully interpreted within the planet's unique geological and chemical context.
Exactly. We would need corroborating isotopic ratios, for instance, observing how biology preferentially utilizes the lighter carbon-12 isotope over the heavier carbon-13. We would ideally need visual evidence of microscopic structural formation.
It's the difference between having a single piece of circumstantial evidence in a trial versus having the forensic data, the physical footprints, and a clear motive all pointing to the exact same conclusion.
The power of this new statistical framework lies in its ability to be a massive, independent pillar of evidence. If visual analysis, isotopic chemistry, and this statistical thermodynamic modeling all independently point in the exact same direction, the conclusion becomes scientifically undeniable.
It strengthens the entire foundation of planetary exploration.
It absolutely does.
As we conclude this, I want to leave you with a final mind-expanding thought to just sort of mull over on your own. We have established that life, according to this new framework, is fundamentally defined by how it statistically organizes information and chemistry. Life is the process that leaves these distinct, quantifiable patterns of richness and evenness as it actively fights against the thermodynamic chaos of entropy.
Right.
If that underlying principle is true, could this mathematical framework eventually be used to detect entirely non-carbon-based life? We are currently entirely focused on organic chemistry, on carbon and water. But what if we encounter something truly exotic?
That's where things get really sci-fi.
Exactly. Imagine a hyper-complex, self-organizing artificial intelligence spreading through a silicon network across a dead world. Or consider theoretical physics, which suggests the possibility of self-sustaining plasma ecosystems existing within the intense magnetic fields of a deep space nebula.
It's a fascinating hypothetical.
If those completely alien entities begin to exhibit these exact same statistical patterns of life, manipulating their surrounding energy and matter to maximize richness and dictate evenness purely for their own structural survival, well, we have to completely rewrite the biological definition of what it means to be alive.
It really makes you wonder if we're just looking for specific chemistry, or if we are ultimately looking for the math of intention.
Exactly. Let that question linger the next time you look up at the vast, scattered chemistry of the night sky.